these two figures. So you might know one, the one on the right, SBF from FTX, but you might not know the one on the left. So the guy on the left is called Luca Pacioli. He's a Franciscan friar that lived in the Renaissance in Italy. He was a close collaborator of Leonardo da Vinci, and is known to the most as the inventor of the double entry bookkeeping standard. So, until today, we use this standard as to write financial books. On one side, you have assets. On the other side, you have the liabilities. This should match. And this concept was firstly introduced by these guys in the 15th century. And the relation between these two people is that the one on the left invented this system, and the one on the right is the one that basically exploited this system to fraud people. And of course, he's not the only one, but this is like, let's say, a general issue of how book authentication works today. So usually, you have on one side, on the left, a company, on the middle, you have an auditor, and on the other side, you have the public, the user, and the public have to trust the auditor that when they say that everything is fine. But there are like two big trust assumptions in this system. So first of all, we have to trust the company that they compile the books correctly. So they are like, they are not cheating when compiling the books. And the second point is the auditor. So we need to trust the auditor that is also trusted and is not cheating, and also is competent enough to understand if everything is working fine or the company is like trying to hide something. So in order to solve the issue with the current book authentication mechanism, we use proof of solvency. The definition of proof of solvency is a cryptographic proof that certifies that a centralized exchange is solvent at a specific moment in time. So there are like maybe two words here that are worth analyzing. First of all is cryptographic. So it has a mathematical nature, is not based on auditors, it's not based on trust assumption, but it's only based on math. And the second point is the definition of solvent. So for a centralized exchange, solvent, not only for a centralized exchange actually, means that the assets must be greater or equal than the liabilities. So let's now see in the case of a centralized exchange, what are assets and what are liabilities. The liabilities are the deposits of the user. So they might be denominated in different cryptocurrency, but the important thing to note here is that these deposits do not live on chain, are only entries in the database, in the server of the centralized exchange. On the opposite side, we have the assets that are actually controlled by the centralized exchange, actually stored within their wallet. And these assets live on chain. And what you basically need to trust is that these assets are mapping one-to-one the liabilities. So whenever you buy a Bitcoin on a centralized exchange, you trust that the exchange is actually buying one Bitcoin and storing it in their wallets. So the role of the proof of solvency is that by verifying this proof pi, the user will be confident, if the proof verifies, they are confident that they can withdraw money from the exchange at any time safely. So that was, let's say, the high-level introduction to proof of solvency. Now we're going to go more deeper into the technical part, into how we design it at Summa. So what we want to achieve is this thing. It's basically same as before, but in the middle, rather than an auditor, we have a proof, this entity that will tell to the public that everything is fine, that the exchange is solvent. So what are the required properties of this proof pi? First of all, it should tell that the exchange is solvent with high probability. So of course, it's like a probabilistic statement. It shouldn't rely on trust assumption. It shouldn't rely on auditors at all in any point of the step, and should be fast to verify for the user. So in terms of time, in terms of size, the proof should be small. And most importantly, it should not reveal data about the users and data about the centralized exchange to the world. So a naive approach will be just to open source the database of the exchange, but of course, an exchange will never do that. So the data that we want to hide, for example, are the individual user information, their username, their balances, the number of users of the centralized exchange. This is a sensitive information for the exchange itself, as let's say business intelligence information, and also the amount of liability of the centralized exchange. So the total aggregated amount of deposit of the user is also something that the exchange won't like to reveal to the public, because it can say a lot about their, I don't know, how they are doing, basically. So how? Now I'm gonna go through the workflow of Summa. There are like mainly 4 steps. One commitment phase for the assets performed by the exchange, one commitment phase for the liabilities, the proof of solvency that is generated by the centralized exchange and sent to a smart contract, and only at the end, the centralized exchange will interact with the user to generate a proof of inclusion. So now we're gonna go through each of these phases. The first phase, I hope that you can see, you can read, is the commitment phase of the assets. It's very simple cryptography. Here, the centralized exchange will sign messages, will pass the signature to a smart contract. The smart contract will verify if this signature corresponds to the claimed public keys, and if so, we'll kind of register these public keys in the smart contract as owned by the exchange. So therefore, all the assets that are controlled by this public key are inferred as controlled by the exchange. The second part is more tricky, and now I'm gonna explain you how. So the second part is the commitment of the liabilities. And for this part, we're gonna use a special data structure that is called the Merkle sum tree. Now I'm gonna explain you how it works. So let's, for example, first of all, we need to think that like the entries in this Merkle sum tree are all the user's entry in the database of the exchange. So we keep it simple, one username, one asset, not many currency. The entry will, like, compared to a leaf in a normal Merkle tree, we not only have the hash, but we also have a balance. So you can see like that each node in this Merkle sum tree stores an hash and a balance. And the point here is like how we build the middle nodes in this Merkle sum tree. And as you can see, for example, in the case of this middle node, the hash will be equal to, the input of the hash will be hash of the left child node, the balance of the left child node, the hash of the right child node, and the balance of the right child node. And the balance will also be the sum of the balances of the child nodes. So the cool thing is that we get to a root that contains a commitment to the state of this Merkle sum tree, and also it contains the balance, which is the aggregated balance of all the entries in the Merkle sum tree. So in this case, all the entries of which are the user of the exchange, basically. So what we do in the commitment phase of the liabilities, the centralized exchange will build this Merkle sum tree locally and will post in the smart contract only the root hash of this Merkle sum tree. So they won't even post the root balance, only the root hash. It's enough. And of course, this root hash won't reveal any information about the state of the liabilities. So now the third part, as you can see, is the proof of solvency. This is the first zero-knowledge proof that we're going to use in our system, and I'm going to explain you how it works. So if you remember, like the idea of proof of solvency is very simple. We need to prove that assets are greater than the liabilities, and we already have, let's say, the commitment to the assets and the liabilities. So we just need to prove that this statement is correct, and we use a circuit for that. We basically start from the penultimate level of the Merkle sum tree. We compute the last level to get to the root hash and the root balance. We expose the root hash as public input to the circuit that will be checked against the one committed in phase 2. And we also check that root balance is less than the sex balance sum that is also another public input of the contract, of the circuit. And it's important to note here that like this input is not actually, it can be hard-coded by the centralized exchange. They can put whatever here, so they can potentially generate a proof of solvency claiming that they control an infinite amount of assets here. But the point here is that the next step, we're going to submit this proof on chain. So the contract will verify that the root hash matches the one committed in phase 2, and also that the claimed balance sum, this value, is actually matching the balance owned by the accounts, the wallets committed in phase 1. So that's how actually we generate the proof of solvency. But there's like a big problem here. Like, of course, this is not enough to claim solvency, because as we said previously, the liabilities are just something written in the database of the exchange. So they can modify it as they like. There's no, let's say, cryptographic binding to the database. So at this point, the centralized exchange can have claimed to be solvent using a set of liabilities in this Merkle sum tree with completely fake entries, fake user with understated balance. So we need a new step in this whole thing, which is a way for the centralized exchange to prove to their users that they have been accounted for correctly in this Merkle sum tree. This is where the last part comes in, and we can use two different techniques to achieve that. A simple Merkle proof of inclusion. So for example, if we want to tell Alice that she's been included correctly in the liabilities, we'll just need to pass her the Merkle proof. She will basically compute it starting from her data and see if the root matches the one committed to in step 3. But there's also another way of doing this. Yeah, I mean, the problem of this is that it leaks data. So Alice will get to know the balance of Bob, and also she'll get to know the aggregated liabilities of the exchange. Instead, what we do is using a ZK proof of inclusion. So this is what Alice will receive, basically, a proof that is just a set of bytes, the leaf hash and the root hash, and she will basically be checking if the leaf hash matching their data, and that the root hash matches the one published on committed to in step 2. So there's no data leaks in this implementation, and this is cool. So this is the structure of the circuit. As you can see, the only public inputs are the root hash and the leaf hash. The private inputs are the username and balance of the user, in this case Alice, and these 3 elements are the Merkle proof, basically. So the circuit will compute the level recursively until getting to the root, and the root will be checked equality with the root hash passed as public input. But there's also another interesting point to take into account here, which is that, as you know, the values inside the circuit are field elements. So there's the risk that if we keep adding together these field elements, we get to a point in which this sum overflows the prime field of our circuit. So we also need to check, we need to perform a range check on the balances, because if this sum overflows, it will basically roll back to 0, and we might end up in a situation that an exchange will end up demonstrating liabilities that are far less than the actual liabilities, just because it rolled back to 0 because of this overflow. So we use this range check in order to prevent this, and we'll see later how this range check chip is designed. So yeah, this is like the last part of the flow. The centralized exchange will generate the proof, the public inputs, pass it to Alice, then will verify it locally, will verify the proof, and will verify that the public inputs are matching the expected ones. And it's important to note here that this type of proof of inclusion needs to be generated for each user. So it's something specific to each user. And the verification here doesn't happen on chain as it happened before, but it happens locally, so it has to be performed locally on the user device. And yeah, I want to lastly, before going into the Halo 2 design, what are our benchmarks? So all the benchmarks have been run by my laptop, and we have considered a centralized exchange with 2 to the 15 users and 2 assets, because as I mentioned before, like we consider an example with just 1 asset, but this Mercosur tree can support infinite asset before, and we get to very good results, I think. It's like a fraction of a second, both for the proof of solvency and the proof of inclusion. I would say the proof of solvency, we shouldn't really worry much about this, because this has to be generated only once for each round of proof of solvency. But the important thing is the proof of inclusion that might be potentially need to be generated for millions of users. So, and this is okay, infinitely parallelizable, but still we want it to be very fast, and yeah, now it's very fast. Okay, so now let's move a bit into the Halo 2 part and how to design the chips that I mentioned in Halo 2. So the chips here is like a smaller component of a circuit. So for example here, I think we can define this compute Mercosur tree level as a chip, this range check as a chip, is equal as a chip, and putting all the chips together, we kind of use them as a sort of processor to build a circuit. I will start with some very quick and non-exhaustive explanation on how circuit development works. The challenge of a circuit developer is to transform a computation into a set of constraints. And not only this, but you need to be careful about how many constraints that you are using, because it will make the prover slower, so more constraint, slower the prover. And also you cannot use if condition and for loops when writing constraint, as you might be used to in normal development. And the last thing is that when you write constraint, you should also cover every possible outcome of the program, of the computation. So you basically need to consider all the possible output and then activate or deactivate some constraint based on the witness, based on the proof that is generated by the user of your circuit. So the mental model is that I use is a grid, and is actually inspired by a presentation that CC gave that guy in Bogota last year. And it's a very, I think, cool framework to understand how to design circuits. So we have this grid. They might also be considered as a kind of an Excel spreadsheet. There are cells in the grid that are filled with feed elements. So as you know, the only elements that are allowed to in a circuit are feed elements. We don't have like Boolean, we don't have these crazy data types, only feed elements. And there are like two moments when that are involved in the circuit development and usage. So the first one is the setup time, where you define constraint. So basically a constraint means a mathematical relation between cells in this grid. And the second moment is the proving time. So after you as a developer develop the circuit, you will basically pass it to prover, to user that will use it, and will use it by filling it the cells with the witness. So the point here is that we need to define constraints such that the prover at proving time cannot cheat, cannot do something that we don't want to in our computation. So maybe this might sound a bit abstract right now, but now we're going to go through a very simple example of a computation, and we are going to compare how you can write this computation in traditional development and in a ZK development, so by setting constraint. So the algorithm is very simple. Here we have an algorithm that takes a flag, and if this flag is true, we return, so it takes as input a flag and 2 numbers, A and B. If a flag is set to true, it will return the sum of these 2 numbers, and if the flag is set to 0, is set to false, it will return 0. So in traditional development, this is really simple to write. It's like this is like some Python code, and you see you have this very easy to use if-else condition, and it will make it work. But so now, how we can express it in a circuit? How can we define constraint for this computation? So first of all, as we mentioned before, we need to define this grid. We'll add 4 variables inside this grid. A, B are the input, the numbers. C is a Boolean, and red is the return value. As I said before, there are not really Boolean types inside the circuit, so we're going to just use like a binary 0 and 1 for C. And the first relation that we want to express, this is actually a constraint. We're basically constraining the output to be equal to A plus B if C is true, or B equal to 0 if C is equal to false. So as you can see, in the case C is equal to 1, return will be equal to A plus B, and if we set C to 0, return will also be 0. And there's also another very subtle thing that we need to constrain inside our circuit, that we need to make sure that C is actually a binary value. So we don't want to allow C to be 10, for example. It must be either 1 or 0. So that's what this constraint does. So it enforces the rule that C must be a binary value. So we are going to see this was only the setup time, and at proving time, the prover will fill in this grid with their witness. And as you can see, if we fill it with like 10, 20, 1, and 30, the first constraint will be satisfied, and also the second constraint will be satisfied. If the prover wants to cheat, for example, I don't know, putting 60 here as a return value, of course, this constraint won't hold true. And also if the prover said like 2 instead of 1, the second constraint will fall. So they won't be able to generate a valid proof. Okay, so now we ended the intro to Halo2, and we are gonna go deeper into the chips that we designed for Summa. The chip that I want to speak to you about is the Mercosur tree chip. It's a very simple chip that computes a level in the tree. So in this example, we are actually taking the first level, so going from the leaves to the first middle nodes, but the same chip can be applied to any level inside the Merkle tree. So, I mean, ideally, what we want to do is just like perform the hashing correctly, and perform the sum correctly. This is the computation that we want to define, and we need to express it to this kind of mathematical constraint that we spoke before. So the first thing that we want to constrain is that the leaves should be placed in the right order before performing the hashing. So it basically just means that Alice should be on the left and Bob on the right, because if we put them in the inverted order, of course, the hash won't result the same, the expected one. We want to make sure that the balance of the parent node, so this 70 is equal to 20 plus 50. We want to make sure that the hashing is performed correctly. So in the case of our protocol, we use Poseidon hashing. So we are going to leverage an external chip, Poseidon specifically, to perform this hashing. And lastly, we want to make sure that the sum doesn't overflow the prime field, as mentioned before. So in order to do that, we're going to need to perform some range check on the input of the sum, and this is also going to be performed by an external chip that, if we have time, we're going to go through it after this. Okay, so this is the grid. Might be a lot to digest, but let's go through it. So first of all, let's just consider these first three columns. So columns A, B, and C. You can see that at row 0, we place the hashes, so the leaf hash and the sibling hash, and there's also this swap bit here. So the swap bit here is just a binary value that indicates whether we need to swap them or not. So if it's set to 1, it basically means that leaf hash needs to be put on the right and sibling hash on the left. Or if it's 0, we just copy this as it was from the previous row. So on row 1, we simply swap these two according to the swap bit. On row 2, we place the balances. So we place the leaf balance, the sibling balance, and again, we have this swap bit that tells us if we need to swap them or keep them in this order. And if you see, there's also something more on row 3, which is the sum. So we also need to consider like the sum between the swap balance left and the swap balance right. So now, this is like how we design the grid. You can decide it to design however you like. And now we can start seeing the constraint that we apply. And by seeing that, you'll see also what's the role of these two columns called selectors. So the first constraint that we apply is a Boolean constraint. So as we mentioned before, similarly to the example that we mentioned before, we need to make sure that this swap bit is either 1 or 0. So we apply this constraint. And as you can see, we say like C cur and C cur. So cur means current row, but current refer to what? So current is referring to the selector. So as you can see, at every row, we have a selector. And if we activate the selector, we are basically activating this constraint. And the important thing to note here is that we don't want this Boolean constraint to apply to every cell in the C column, because, for example, at sum, we don't want it to enforce it to be either 1 or 0. So at that row, this Boolean constraint that is activated by this bool swap selector will be set to 0. So if we set this to 0, we can see that like this equation will always be satisfied. But for example, in row 0 and in row 2, we want to enforce this constraint, so we set the selector to 1, and whenever this selector is set to 1, the second part of the equation must be true, and this is the part that enforces this swap bit to either be 1 or 0. So this is the first constraint. The second constraint is the swap constraint. I think this is not like super important to go through the details of this equation, but it's basically just enforcing the fact that if swap bit is equal to 1, the swapping between row 0 and row 1 is performed correctly, and if it's set to 0, again, it should be performed correctly just by copying the value from the previous row. And again, you see that this is enabled by the bool swap selector, because, for example, at this row, we don't want to enable this constraint, so we set the selector to 0. And the last constraint, is the sum constraint, which is the one that enforces that this value, the sum of this value and this value is equal to sum. And again, this needs to be performed only at this row. So we need to tell the circuit somehow to enforce this constraint only at the specific row. In order to do that, we use the sum selector that is only activated at row 3. So this is not everything. We also need to apply some other constraint. For example, we need to check that swap bit is the same. So we shouldn't use, 1 here and 0 here, but we should be consistent because it's basically the same level of hashing. So here we enforce a copy constraint. That is another type of constraint. It's not like those before are technically called polynomial constraint. This is maybe a simple type of constraint that is just enforcing two cells in our grid to be equal. Another constraint is that we need to pass these values to the hasher, to the Poseidon hasher. So, in particular, we pass the order of passing will be swap dash left, swap balance left, swap dash right, yes, and swap balance right. So as you remember before, this is the order of the hashing, and we need to pass this value to the hasher in the correct order. And the last thing, as we mentioned before, is the overflow. So we need to check that this swap balance left and swap balance right do not overflow. So we'll pass this to the range check chip. I think we do have time to go also through the range check chip. So the role of this chip is to check that a value is in a required range. And in this example, we'll take the range is simply 16 bits. So we want to make sure that the value in the cell A at row 0 is 16 bits. And the way we do that is decomposing this value in 8-bit chunks and add these chunks to the column B. So in this case, how will the grid look like? So again, we have we have two columns, A and B. I think this is clear. We have two selectors that we're gonna go through their meaning. And we also have a new thing that is a lookup table. So a lookup table is basically a fixed table that is defined at setup time. We define at setup time the values that are inside this lookup table, and we can later perform lookup check. That we're going to see now what they work. So the first type of constraint that we want to apply is basically we want to make sure that like this value, so let's say this value multiplied by 2 to the power of 8 plus this value multiplied by 2 to the power of 0 in this case is equal to A. So we want basically to make sure that the decomposition of A was performed correctly. And this is done by this constraint here, and the constraint is activated by the decomposed value selector. And as you can see, the selector is only activated at row 0 and is taking the current cell in the column B and the next cell in column B relative to the row in which the selector was activated. So of course, we want to activate this constraint in this row because there's no A, it's like empty. So it doesn't make sense. It will fail actually because this is 0. So this is the first type of constraint that we want to apply. And maybe it seems enough to check that the value A is in the required range, but that's also another subtle thing that we need to make sure of, that we need to make sure that each decomposed value is actually 8 bits, because otherwise we could place like very big values in B, and maybe this the first constraint will be true, but still without A being in the 60 bits range. So we need to make sure that each of these values is inside of 8-bit range, and we do that using the lookup table. So as you can see, we fill this lookup table with values from 0 to 255, so all the values in the range of 8 bits. And the lookup table will simply be looking if the value B is existing in this table. So maybe it's a bit confusing, then here I use hexadecimal and here decimal, but you get what it means. And again, we have a selector that will activate the lookup only when required. So in this very small case, it's required at every row. So good. So yeah, this is basically how we define the range check chip. Before getting into the Q&A session, I also want to describe a few open challenges that we have in our protocol. So the first one is the private information retrieval for proof of inclusion. So as you might have noted, the soundness of a proof of solvency protocol rely on the number of users that verify the proof that was generated to them by the exchange. So if a user never verified the proof, actually the exchange can potentially just exclude them from the liabilities tree, and they will basically go undetected. They could cheat without being undetected because they know that this user never verified the proof. But how would they know if a user verified the proof or not? If we use, let's say, a protocol in which the user has to request in an express way, in an explicit way to the centralized exchange to fetch their proof, but basically like the exchange will end up knowing the list of users who verified and the list of users who never verified it. So private information retrieval would be very helpful for us to let user retrieve their proof of inclusion without the exchange having to know which user performed this action. So this is a topic. Also another topic that is very important for us is the privacy on the asset of the centralized exchange. As you remember, like the commitment to the assets is public, so they will just share their public key and everyone will be able to see that. But what we would like to achieve is a private proof of assets. But today we cannot really do that, because if we use signature as a way to authenticate centralized exchange, like the SCSA signature in the case of Ethereum, I mean, of any blockchain that uses CDSA as authentication mechanism, these signatures are non-deterministic. So we cannot use the signature to nullify a signer, and if we cannot nullify, there are chances that this same proof of assets is double spent by different exchanges, and we don't want it. So we are basically trying to find ways that allows the centralized exchange to prove assets with privacy without asking them to give up their private key, because, okay, we could ask their private key and use this as a source of the nullifier, but they don't have access to the private key. Like a centralized exchange might have this distributed, or they might have all of these security measures. So yeah, this is an open challenge, and if you have any ideas on that, I'm happy to discuss. And lastly, yeah, I want to leave you two QR codes. One is our GitHub, where you have all the codes, and the second one is a Discord channel where we discuss stuff related to Proof of Solvency. So yeah, my presentation is done, and I'm happy to take any questions.
Thank you, Enrico. If there are any questions in the audience, I will bring the mic to you. Yeah.
Yeah, so just, I was wondering if, really good talk, by the way. I was wondering if you looked at the sapling key structure, where they do this sort of key structure where you can compute nullifiers without the private spending key. So, just relating to what you said, that you need the private key to compute the nullifier.
Yeah, no, I haven't looked in. It's like a paper, the one.
So there's just if you look at Zcash spec, you Google that.
Yeah.
So there was this design where the key to derive the nullifier has less power than the actual spending key. So yeah, maybe.
Okay, no, I haven't looked into that. So it's yeah, thanks for the proposal.
Thank you. So the user, when you want to verify, they know their balance, and then they can check the proof. But what about the assets part? No, they can make up that database by themselves.
Yeah, I mean, like for the asset part, as soon as this is public, the exchange cannot really make it up. Like the thing is that this rely on a signature. So the assumption that we make is that as soon as the exchange perform a signature on a specific message that we ask them for, then they control these assets. Of course, we can say that, like, yeah, they could cheat, they could ask their friends to sign a message. But the point is, I think a good thing of having the proof of assets public is that these addresses can be monitored. So we can tell if something shady is happening between this address, which might be more difficult to do in the case of the private proof of asset. But I think on the asset side, we are quite safe that they are not doing anything suspicious or malicious. But I mean, if you think that there's some bug or something that we didn't consider, it's good if you can point it out.
Hi, thanks for the talk. Probably I missed some details. My question is, how do you check overflows over the prime field? Because what I've seen that you decompose it in 8 bits, whatever, but you don't know if the A value has overflowed, underflowed, you know.
Yeah. So it's like like what we are doing is, so let's consider like a situation in which let's say in our case the prime is between like 254 bits and 255 bits. So we set a range arbitrarily. We can set it to 248 bits, and in this case, basically, what we are checking is that A. Okay, let's take this as an example, just 16 bits. The way we check that A is in 16 bits is that we make sure that like its decomposition is, you can decompose a 16 bits value using two 8 bits value. So if A was beyond like the 16 bits, it wouldn't be able to decompose it in 16 bits value. So I understand your question, like maybe A is already an overflown value. So yeah, the point is that like if we consider like we do this to all the entries in the tree, so as long as each entry and each balance that we check before performing the sum is inside the range, we make sure that it never overflows. Like the only thing it can happen is that it has overflown before entering in the tree. Sorry, in the circuit. So if we pass 255 values, 255 bits value inside the circuit, it will be overflown from step 0 basically, and in that case, this will actually pass the proof. Will be generate a valid proof, but the user in that case will see that their balance is mismatching. So when we pass a proof of inclusion to a user, they will say, hey, I mean, like I had like 2, I don't know, million, and then now it's overflown to 1. So that's something wrong. So we perform the overflow check at each entry's balance, and we perform the overflow before every sum inside the Mercosur tree. So that's how we avoid the overflow. But we cannot avoid a value to overflow before even entering the circuit. This will be spotted by the user verification of the proof of inclusion.
If I understood it correctly, for example, if you have two values, FF and 1, they will pass the check, but when you sum, they will still pass the check because it will be 0, 0, for example, if it is between 0, 0 and FF. But then it will fail some other constraints on balances and so on.
Yeah, exactly. So let's consider, for example, if we want to perform, so A is just, we want to perform the sum between two values. Okay, it's A and B. At step 0, they are like the closest value possible to 16 bits. So A will be in 16 bits, B will be in 16 bits. But at the next step, when we sum them together, then we get to a value that is more than 60 bits. So the next overflow check in the sum, that will be at the next level of the tree. So when this won't be the parent nodes, but this will be a child nodes, this sum will fail the overflow check. Yeah. I mean, not much slow, just 1 bit smooth. Yeah.
Okay, let's wrap this session up. Thank you for the discussion, Enrico. And if there are any further questions, we can take them offline.